Okay, hi everyone. So last time we finished the lecture by stating the main result, arithmetical completeness theorem. Now I repeat it here. So in the system GLP, formula phi is provable if and only if for every arithmetical translation F, arithmetical translation, the other arithmetic proofs phi F phi funny. And this holds for all phi strong sequences of probability predicate in the theory T, where T is sound and contains P, like that. So we are working over piano arithmetic in the first order arithmetical language. We have defined the notion of a sequence of strong probability predicates. And basically, this means that so pi is sequence of arithmetical formulas, right? And each one of them is sigma and 0, sigma and 1, complete in the corresponding class of the arithmetical hierarchy. Certain properties are assumed, essentially the Loeb's condition for each of these probability predicates, as well as sigma and I completeness property. So that's the situation. And we also assume that provably something like A proves that I of x equals x1 of x, let's say uniformly for all x, something like that, for all formulas alpha to which these predicates apply. So that's
can you remind me which role the T plays? Because everywhere else only PA.
Yeah, in fact, this works. Let's do it simply. So let's say that we have, so everything is within T there. So the probability predicates, they are over T itself, right? So let's say T is that they are included. And yeah, better to say over T. So each one of them corresponds to its own theory, which extends T and very strongly extends T, but their properties are verifiable in T. And T is some fixed system. For us, it can be just piano arithmetic, that's it. And we cannot somehow, for this theorem, we don't know whether we can weaken it to anything substantially weaker, even I sigma 1. And that's
even I sigma 1 is not.
Even I sigma 1. If we want to full completeness result for the.
What is the issue there for which part?
Collection. So the issue is that Soloway construction presupposes in this relativized form some sigma n collection principle for for every ni, and then it goes out of hand, so to say. This is the problem. So we want to prove the theorem. We essentially explained the so-called easy part from left to right. So that is more or less the condition on the probability predicates that we have. And this interesting part is the other direction, and we will go about it in contrapositive form. So we assume that GIP does not prove phi, And then we say that there should exist an F such that P does not produce of phi. So that's the result we would like to prove. And we need some intermediate steps that will help us. And one of them was this system model logic J that I would like to write out here. So these are the sublogic of GLP, which has nice script key semantical properties. And so the axioms of J are essentially the familiar axioms of Gödel logic for each n. Right, so that's Gödel logic. Then we will have the key principle. I think it's best to keep that m is always smaller than n. So I will formulate it like this: m is smaller than n. This can be left as is, but also n phi implies box n phi, or m smaller than n. We can also postulate here smaller or equal if we like, so that's, but this then will be the usual transitivity principle which follows from the first two axioms, but okay. This is assumed, and the negative introspection, where really we need a strict inequality. So, and the rules, mod exponents, and profile infer. So that's the system J. As I said, so J is complete with respect to nice Kripke frames, and Kripke frames can be characterized by a number of, so these are relational structures. Where our I are well-found upward, Noetherian, right? Binary relations, so no upwards, infinite upwards increasing chains. Transitive. So that's covers essentially the validity of these two principles. Now, these two principles, they amount to the following polytransitivity, property that I call polytransitivity, which is if we have our, we can write it like this: Rm is contained in R minimum of n. In other words, if x, Rm, y, and z, then x then x rkz, where z is this minimum of k is the minimum of m and n. So this is essentially what these two principles say. So if you read them conversely, so diamond m implies diamond m, and so the minimal of them will be sort of selected in the end, regardless of the order. So that's a kind of nice property. And
Sorry, what is the connection of K and M and N?
K is the minimum of M. It's just the same thing written here, just for simplicity. And this property corresponds to the more interesting analog of so-called Euclidity. So if you have X are M, Y, and X are N, Z. So if X sees both something labeled N and something labeled M, and this is X, this is Z, and this is Y, where M is smaller than N, strictly smaller, then one has the arrow from here to here. Right, so this is a little bit abstract, but this is a complete keyframe semantics. So one can show that the formula is provable in J, even only if it is true in all these structures, even finite structures. One can draw a slightly more intuitive picture of these models, which will be in fact a subclass of all structures like that, but it is also sufficient for the completeness of J. So I call them hereditary trees. So suppose you have a structure which is a finite tree, like that. So that's, we call it zero, something like this. But then we expand it like this. So we now consider every node of that structure, every vertex of the tree. So trees are partial orders, even strict partial orders, as in that situation. So now we have here, imagine that this is a kind of a flat piece of flat paper, sheet of paper on which we draw another. Let's take some orange color. So some other finite tree completely out. There are no relations between these two trees living in different worlds, so they're not included in one another. They're just like a set consisting of sets, but there is no restriction. So this will be the sort of one trees. And of course, this orange relation. So this, in the sense of these keyframes, this will be representing R0 relation, but this will be representing R1 relation. So all the arrows and their transitive closure will be the R1 relation. Now, what happens more specifically? So so these are equivalence classes called one sheets, and these equivalence classes are discrete with respect to relation 0. So the points here are not connected by 0 in any way. They're connected by 1 as depicted. And it is meant that 0 relation now connects every point here with every point here. So 0 relation is a kind of bipartite sort of thing where this subgraph is discrete and this is discrete, and then they connect everything. So it's a kind of, yeah, you can say dependent sum of one trees along the 0 relation, something like that. So this is essentially the model of the system denoted J1, consisting of with modalities Vox 0 and Vox 1. And of course, J2 will be obtained by a similar kind of operation. So you take a number of one trees, connect them with relation So essentially here you will see these little structures. And this will be now two trees living in these subclasses, etc. So that's the structure of a typical model of the system J. So that's how we can envisage them. It's convenient to think about them in this way, which also suggests somehow the way the solar wave functions will be organized in this arithmetical completeness proof. So the first, let's proceed with our argument. So the first part of our argument is somehow to come from GLP to J, and this is with the help of these formulas. So let's define these notations. So essentially, we need a formula accumulating all needed instances of the remaining monotonicity principle of the axiom of GLP. And yeah, so let's see. So right. So so M of phi is the formula which is a big conjunction of all the instances So firstly, we keep the list of all subformulas of phi of the form box something, beginning with some modality. So these are all subformulas, all modelized, let's call them modelized. Formulas of the formula phi. And n here is the largest largest modality. No, so those three. So every other modality occurring in phi is less than this specific n, so we fix it for the rest of the proof. So phi is a given formula. M of phi is just a bunch of instances of monotonicity axiom. It is finite because we have finitely many subformulas. And we sort of take any such subformula and formulate the instance, all possible instances with j bigger than mi, right? So, but up to n. We don't need anything larger than n. So that's one thing. And so I is from 0 to s. So these are all subformulas. So that's like that. Now m plus of phi is the formula saying that M of phi will be true everywhere in our Kripke frame, in our Kripke model. So M of phi is a formula M of phi and conjunction for I smaller than n, box I M of phi. So we say that M of phi is true and box of M of phi is true for every I smaller than n. Now, the effect of this formula is that if we have, let's say, if we have this, this means that everywhere reachable, let's say, reachable. No. X W M phi is true. So M of phi, M plus of phi is true in X, even only if, not only in X we have M of phi, but also in every other point that can be accessed from X by some path within our model. So that's a reasonable idea. And now we have this. Now we have this obvious lemma. If G of P does not prove phi, then there is J model W and a point R such that in this point R, the formula M plus phi is true, and phi is false. Yeah. So why so? Because obviously, if this does not hold, then J does not prove M plus of phi implies phi. If it did, we would infer in GLP the formula phi, obviously, because all these formulas are just essentially instances of axioms of GLP. So if GLP does not prove phi, then J does not prove this. And if J does not prove this, then there is a model W falsifying this at a certain point. And that's what is written here. So completeness theorem for logic J gives you this result. Yeah.
So what is, so the J is what's written there, right?
Right.
What is the difference between J and GLP?
Yeah, the presence of the monotonicity axiom. So GLP is J plus box M phi implies box N phi. Very simple.
Okay.
So what we did, we threw out this axiom. We threw in some of the consequences of this axiom. So in the original shorter formulation of GLP, not all of these formulas were present, but there were theorems. So then we can sort of say, okay, we assume that GLP does not prove phi. We want to have some sort of Kripke model falsifying phi, and we obtain a model like that. So we say that J does not prove that in M plus of phi implies phi, and then there is a model, J model, falsifying this formula phi and satisfying the principle M plus of phi. Right.
Yeah, and so they're on the right. So these are just the cryptic claims that like are appropriate for J, right?
Right.
And we just say this without proof.
Without proof, yes. It's a separate part of the proof.
Yeah.
We say it's a pure model logic, therefore easy.
Okay.
Right. It's not always the case that pure model logic is easy, but
Yeah, the GLP stuff.
but in this particular case, we have the right to say that. So it's not much different from the completeness theorem with respect to Kripke models for Gödel logic. So it's essentially similar kind of statement. No difficulties there. So we go from phi is not provable in GLP to somewhat bigger formula not provable in J. And then we have our model. So that will be the model we will be working with. And we also can assume that R is the root of this model. In other words, every other node in this model is reachable from R, because these non-reachable nodes, they are not needed for the evaluation of any formulas, so we can just safely throw them in. So we call this R is sometimes called a hereditary root, because where does this root occur in this kind of picture? Well, every tree has its root, and then the tree in this root also has its root, and then we go to the root of every root of that structure, and somewhere here there is a single point R, which sees all other points by some of the relations. And that's our crucial point where the formula phi will be false somehow. But we all have an additional piece of information, namely that instances of monotonicity axiom are true everywhere, at least when restricted to subformulas of phi, something like that. So that's what we have. Okay. And now we would like, of course, to construct our arithmetical interpretation F, evaluation F, so that the resulting sentences will be unprovable, and that's the central part of the arithmetical completeness proof. So we take this model as given and now define the Solovay functions in such a way that everything works. Now, in order to fortunately, in this arguments, we can cleanly separate the conditions that we need to achieve in order to obtain non-probability, and then the construction itself that will achieve our conditions. So, and here is the main lemma, for which we also need one model piece of notation. So let's define the set of all nodes accessible from X by the relation Rk, by Rk of X. So that's the set of all Y such that X Rk Y. Then we have Rk star of X, and that is the set of all Y such that X Ri Y for some I bigger or equal than K. So if we think about this picture, so what is it? So suppose we are somewhere in this point. So nodes that are reachable by zero relation occur everywhere in this upper part of the model. So by zero we can reach any point here from that point. But by zero we cannot reach anything in this lower part. So it's discrete. But if we take one is bigger than zero, then from that point we can also go using one relation somewhere, and we cut out a little tree here above that node. And by the way, also notice that X does not belong to Rk of X because it's irreflexive, this relation. So it's always points to something above, not equal to X, as well as here. So that's a similar situation, but we have more nodes here, also in these hereditary parts of our frame. And finally, there is this notion R tilde K of X, consisting of Rk star of X union with big union Rk star of Z such that X are such that x in R k plus 1 R of z. Right. So let's think about what it is. So it actually includes certain nodes that could be below x. For example, again, let's think about this node x here. So this is all this is automatically in R0 star of x, and also this thing is in R0 star of x. But then we take, so these parts also belong to tilde. But then we add a bit more. So we take any nodes z, such that x belongs to the rk plus 1 star of z. So nodes z from which you can see the node x. For example, this node r here, it's a root, and x is reachable by r1 from x, from r. X is reachable by 1 from r. So that means that rk star of z will also be included, something like that. So that's the idea. So or am I slightly wrong here? So k for us here, let's say k is 1. Right? So if k is 0, then R0 of x indeed consists of, no, it's all right. So it's exactly as I said. So then x is reachable by R1 from R. So essentially everything above the root of that lowermost sheet will belong to R tilde k of x.
That lowermost sheet already included in R star. But you are
not completely. So it's part above the x. It's part above the x. So let's say k is 0, I is 1. So we take everything which are reachable by R1 from x into star, but not until then.
But the one relation is assumed. Okay.
One relation is orange relation on the tree, and x is hanging somewhere in the middle of that tree. So it's So basically, we take everything in that lowermost tree from which x is reachable. So to say that's So we take almost all the nodes in this sheet from which we are looking at all this. So anyway, so that's the notion, and then we want to state these conditions. So let us see whether we can. Yeah, we probably can. So what we want to do is conditions. We want to define a family of arithmetical sentences. So for every x in W, we associate an arithmetical sentence as x. So arithmetical sentence. Yeah, and also, as often in the solver reconstruction, sometimes one needs to add one more root. So we have this model, big model W, and its hereditary root R, where the formula of R is false. And then for the construction, we will add one more root, which is denoted usually 0, from which everything it will be. So visible by the relation R0. So that's a kind of lowermost zero sheet consisting of a 1 point, something like that. So we assume that this is 0 is also present. So we assign to every node in W0. So W0 is W0. So that's the how I denote it. Okay, so that will be the goal of our construction. And then we will define evaluation of propositional variables as always, as disjunction for over all x in which P holds. Formulas as x. So essentially, the arithmetical sentence corresponding to the variable P will say that one of these Sx is true for some x where P is 2, something like this. So that's the interpretation. And then reading this, we will need the following condition. Condition S1 is that in our theory, call it he proves the disjunction of all of them as x, and they are pairwise incompatible. So these are the sentences which are totally disjoint, probably in our basic system T. So that's one requirement. It corresponds to the idea that these sentences, they model the situation in our Kripke frame. So there are points in our frame that correspond to sentences as x, and there are sets in our frame that corresponds to model formulas, and they correspond to more general propositions in our model language. So we assume that the points are sort of totally disjoint and maximal in this. So it's like atoms they correspond to atoms in our Boolean algebra.
So can I ask a question? Is 0 is a reflexive root or irreflexive in our new model?
Irreflexive. We don't.
Mhm.
We just don't care. So far, we just added one root. Yeah, one more point. Yes, it's at this point it's very technical, so it doesn't have any particular meaning. So when we deal with the second version of Solvay theorem, then it will indeed be a difference if it is reflexive or not, but so far not. Now S2, condition S2 is the traditional condition of Solvay construction. So Sx implies not provable in the sense of K provable, not Sy. So for Y is for all Y RK X. In other words, if Y is reachable by RK from X, then we postulate this condition that Sx implies consistency with respect to probability of K of the sentence Sy. So it's like they say, Sy is consistent. If Sx, then Sy is consistent. And condition S3 is now the condition that T proves Sx if Sx, then it is provable in K. And then the big disjunction for Y in R tilde. So here we use this tilde. Sy for all x different from 0. So that partly explains why we needed 0 here, because the construction will allow us to achieve this only for x different from 0, but we want it to be satisfied in the, let's say, contextual part of our model, not the simplest way to achieve it. So that's, you can say, the novelty of this Japaridze construction is that here we have this different condition. So in the traditional Solvay construction, so imagine that there is only one probability predicate K or 0, then this would imply that Sx implies proof 0. Y belongs to R tilde 0 of x, but if there is nothing else but 0, then this is simply R of x. So R star is the same as R, and that means that, then this reduces to the ordinary Solvay construction condition. And here, this is an adapted condition for this for the type of models we deal with. So that's the thing. So now let us prove the theorem from lemma. Right. Maybe I forgot one more simple condition. For S0 is true. So, all of these Sx's are in fact false, but S0 is the one which is true. So, okay. So let us infer statement of the theorem from this, and this is achieved by this lemma, by some lemma. You can say main lemma, or main commutation lemma, or embedding lemma. So for all subformulas theta of phi, and all x in W0, we have these two statements. A, and that's if x, if theta is true, then P proves as x implies phi of theta, and B, if theta is false, then T implies x not phi. Right. So this is this is a statement. Now, if we manage to prove this lemma, which we will in a second, so in a minute, we can conclude that the theorem is true because why? Because the formula phi is false at the node R. So we will have by the item B, we will see that T proves SR implies not F of phi, right? So that's a consequence of lemma. And then what we need to show is that T does not prove F pi of phi. So we can reverse this, and then it means that f phi of phi implies not as r. So if f pi of phi is provable in T, then we would obtain that T proves not as R. Right? But if T proves not as R, then look at this condition. So we would say that S0, okay, T proves that SR is provable. Because T is the weakest of them, of those probability predicates. So it is provable. And then by condition S2 with K equals 0, we would obtain that provable not as R implies S0. All right, so implies not as not as 0. So this one implies not as 0. Right, by condition S2, which means that T proves not as 0, but as 0 is true in the standard model. So our system T is not sound, but we assume that it is sound. So like that. So mostly, so as you see, so all this was needed to infer this particular consequence for phi. But now let's prove this this lemma because by an inductive argument. So let us prove the lemma now. Okay.
Have we proved that such sentences satisfying conditions exist?
Yes, we will prove it later. So that's the main part. Yes, but so far we have not even yet finished our proof that these conditions imply the theorem, because we need to prove this lemma. Right? We inferred theorem from lemma, but we now need to prove the lemma. So let's prove the lemma. Induction on the buildup of the formula theta. And of course, for variables or falsity, this follows from condition S1. Because suppose theta is a variable, then interpretation of the variable is this disjunction for all Sx in which this variable is true. So, but Sx is one of them because theta is true in X, so it implies. So theta variable or top or bottom, and then we refer to condition S1. Now, if we consider the case of Boolean connectives, let's say that is theta 1 and theta 2, then it reduces by induction hypothesis to theta 1 and theta 2. We used the induction hypothesis without any trouble. Negation also works because we prove A and B simultaneously. And so that's the argumentation. So the key point is when theta is box theta 1 psi, box psi. So box K psi. So let's consider these two cases separately. And starting with B because it's simpler and similar to ordinary solving construction. So suppose X is box K psi is false. This means that there is a Y in Rk of X, right, such that in Y the formula psi is false. By the induction hypothesis, it is provable that Sy implies not Fy of psi. Psi is shorter than theta, so it's like that. And then we can just use the standard kind of argumentation. So if it is provable in T, it is also K provable. So then T proves that provable K Sy implies provable K not Fy of stars, like that. I was rather I did it the other way around, so maybe
The contraposition.
the contraposition. So let's do it like that. So indeed, so here we need to say not, here we said F prime of psi, and here we say not Sy, like that. Right. So it's a bit similar to this reasoning. In fact, it's the same reason. So so this holds, and then we have that T proves that this thing implies not Sx, right? By which condition? By S2. By S2. By S2, we have that this implies this. Therefore, by contraposition, again, we have Sx implies not provable K F Phi of psi. And this is
Desired.
yeah, the desired formula, not F Phi of theta. Graphically equal, that's my way of writing it. So, so that completes this case B for the crucial case model formula. And now here comes the next part. Let's do it like that. For the proof of A, so assume Wx, the formula theta is box A psi is true. Now, claim. So we claim that something more can be now stated. So now we use the properties of our model, the particular structure and particular evaluation. Namely, we claim that for every W from this R tilde K of X, W where is the formula psi. And clearly this is sufficient essentially because of the last condition, because if we prove that, we are essentially done. But let's prove this. Yeah, so assume that W is in R tilde K of X. Then for some z, we have two things, that x is in the union with r star plus 1 z, and w belongs to r k star of z. So that's essentially the definition of tilde, right? So if we say that w is in rk tilde of x, then either it is in rk star of x or in these things. But these two cases are combined into this kind of statement. So there is some, so either x belongs to, so there is some z such that x belongs to, such that w belongs to rk star of z, and x belongs to, x is either z or rk plus 1 star. So that's more or less restatement of the definition of tilde. Restatement of the definition of tilde. Okay. Yeah, then we have the following for every y from rk on x. Right, so here we essentially are in this situation. So either z is x or x belongs to rk plus 1 star of z. And so this, if z was x, so what we have is this. So this is what we start with. That was given to us by the condition that formula box k psi is true at x. So that's and everywhere above x with respect to rk we have psi. So that's what we have. But then we have this z, and for this z we have that rk of z equals rk of x. So if z is x, this is obvious. If x belongs to rk plus 1 star of z, then they are connected by some relation which is bigger than k plus 1. And there was this Euclidean property of our model. So we have this situation. So this is the point y, and this is the relation between y and z and x. So that's so if we have if x belongs to rk plus 1 star of z, then this must be the same set because they see the same points. So there was this this condition, right? Which means that also in rk of z we have the same. So w z. We also have the formula box k psi. So z and x are looking at the same set of nodes by the relation rk, and everywhere there psi is true. So in z we have box k psi. And now we refer to this m of phi, right? So in z we have so in z we have this condition that box k I implies box M psi for M bigger than K. Therefore, we also have, this is true in Z, therefore in Z we also have box M psi for all such M. For all such M. Yeah. And in fact, for M bigger or equal than K, because for K this is trivially so. But we see that W belongs to RK star of Z, right? So so we obtain that in W, the formula of psi must also be true. Right, so that's how it essentially works. So we have shown that in all such W, we have our formula psi. And now we can just finish our consideration. So, so we have proved the claim. We have proved the claim. And now from the claim, we of course have that, okay, for all W, the formula psi is true, which means that our theory proves that the disjunction of SW for all W from R tilde K X implies Fi of psi. So for every particular W, we have that SW implies this formula, therefore the disjunction of all of them also implies this formula. And then we can prove with the provability. By the usual loops, by the derivability condition. And we can even say that Sx implies by S3. What was needed? Right. So basically what we did was the following. We assume that this formula is true, then using the specific features of our model, we obtain that apart from being true in X, this formula should be true in many other points in our model, mostly on the same K plane as X. And having done that, we actually, it allowed us to somehow use this weaker kind of condition to still obtain the necessary commutation. So that's basically what basically the claim. So we now we have finished the arithmetical completeness proof with all the details, modular construction of these sentences Sx, and this is the last, if you like, the last step. So let us let us there are so many constructions. That is, of course, the most difficult. I would say dividing these conditions in general setup is kind of logical, right? So there is a feature of this proof is that it is not arbitrary. So in some sense, it goes. So the theorem, the claim of the theorem, more or less forces on us this kind of conditions. Of course, it matters how we arrange specifically with what kind of models we work, but more or less these conditions are forced on us by by the claim of the theorem. And now here there's the difficult sort of model, how to build them. And okay, what we will do is using, of course, the Soloway idea. And now we will be defining the functions hk so-called Soloway functions or sequences from natural numbers to the nodes of our structure. And there will be finitely many of them, so k will be from 0 up to that, and that was the maximal modality that we consider here. So, so we will simultaneously define finitely many n+1 many functions. And essentially, the definition is recursive. So we first will say that our sentence Sx will be defined as a certain limit statements, right? So n or n. Now it is suddenly this maximal modality. Let us denote it L. And n will be the parameter of the function. Okay, very good. So it is the statement that the limit of the nth function is x. In other words, the statement that there is an n0, such that for every n bigger than n0, h n where hm is the formula defining the graph of the function n. Something like this. But our functions will not be recursive or even computable. So essentially, this hm will be an arithmetical formula of appropriate complexity class. So it's therefore we are sort of thinking of them in terms of arithmetical formulas. However, the map from x to the number of Sx, this thing will be primitive recursive, easy to compute, and so on and so on. So correspondence between these sentences and the nodes of the model, which is finite, will be very simple. So this is also good to have in mind. Remember that this is a limit statement. And now here is a definition. So we sort of define h0, 0, 0, and hk of 0 is lk minus 1. So the zeros, function number 0 begins with the bottom, and function number k begins in the limit of the function k minus 1. And of course, already this condition is not recursive, because even if h0 is recursive, we cannot compute where its limit will be, right? So that's but we can state this as an arithmetical sentence of complexity sigma 2, I guess, right? So something like this. And step behavior will be like this: hk of n+1 will be equal to, goes to z if hk of n rk d, and So if at step n we receive a witness of the probability of the sentence not as z in the sense of k probability. So the rule of thumb is that the function number k is reacting to the proofs in the sense of case probability predicate. And as soon as we receive a proof of something that the limit is not z, we go immediately to that point. So that's exactly the Soloway function style behavior. So the only difference with the canonical simpler Soloway construction is that there is only one function h0. It begins with 0, so there is no this condition about where the following functions should begin. So the only difference is that we specified the new kind of beginning for them. And if no such z exists, then we just remain at the same point. If no z exists. So if at step n nothing happens, or we receive the proof of some different statement, so we just do nothing and remain there. So that's the thing. Now one can think about how to correctly apply the arithmetical fixed point theorem in order to define all these functions, because of course each of them is referring to the sentences of the form SZ. So in particular, it refers to the function number m. So even the function number 0, in fact, refers to the 0 proofs, ordinary proofs, but of statements referring to the last of these functions. So it's not that one can first define the function h0 by a fixed point, define it, then define h1, define. So that's not how it works here. So they all refer to the last function. So, but basically you can unwind this definition starting from the last function. Instead, for example, hm is defined in terms of m proofs of the statements, limit statements for the function hm itself. So it's like really the ordinary Soloway function that will be the last function here. So you first define the function hm a la Soloway, but relativized to the class, appropriate complexity class sigma n. Then you will be able, having defined hm, you have already defined the sentences as x, and then you can substitute it into the definitions of hm minus 1, blah, 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 up to h0, and that's one way to define all this correctly. So that's not really a big problem. And now let's just deal with these conditions. Right? So deal with these conditions. So we need to somehow speak about these conditions and convince ourselves that we do have something like that. So, okay. Right. That's enough time to finish. So we're nearly there. So, yeah, so let's see. Condition S1. Clearly, the limit of the function hm exists because these functions only follow the arrows of the model. Each one of them is irreflexive and transitive. So eventually hm reaches its limit. So we can actually prove that h0 reaches its limit, h1 begins with that limit and then reaches its limit, and h2 and so on up to hm. So the limit exists. This is this statement, and the limit can be only at one specific point. That's the second statement. Limit is unique. So all this is clearly provable in piano arithmetic. Now we come to more interesting condition S2 and S3. So let's see what we can say about condition S2. So this is again quite similar to the standard Solvay argumentation. So let us be careful about it. So condition S2 saying that if Sx holds, the limit Lm is x, then it is not possible that Sy is k provable for y reachable by k from x. Okay. So we reason as follows. So assume Sn. And then what we can say about Lk. So we need to step down from Lm to Lk. So the m's limit is x. What can we say about the k's limit? So the k's limit has been reached before the function hm even starts moving, so to say, right? So it starts moving from the limit of Lk. So we can say that in this case, Lk is x, or x belongs to R star. K plus 1 of Lk. Like that. So the limit number k can be x because maybe before, maybe the m's function did not move starting from. Or it must be reached, Lk must be reached at a certain point after which our function makes only jumps according to the relations with numbers bigger than k plus 1. So the function number k jumps along Rk. So and after reaching the limit for Rk for Hk, then the k plus 1 or bigger relations are activated, so to say. But in both cases, we have that Rk of x equals to Rk of Lk. Then let n0 be such that for all n bigger than n0, we state Hk is that limit point Lk. So at a certain step n0, the function Hk reached its limit Lk. And then assume that it is provable. Assume that it is provable that not Sy for some y from Rk of x. Then we can select a proof which is bigger than n0. So there is an n1 such that here is n1 not Sy, and n1 is bigger than n0. And then we have the condition for the jump, because we are now sitting at stage n1. We are sitting at the point Lk. So Hk of n. equals LK. So after N0, HK sits in LK, and N1 is bigger than N0, so it must be in LK. So we are sitting in LK, and we see a certain point R, which is from RK of X. But this is the same as being from RK in LK. So LK also sees the same point, and that means the condition for jump is satisfied. So jumping case in the definition of HK is activated. HK must jump. Jumps. It doesn't even matter where. But as soon as it jumps, it violates the assumption that it cannot jump. So this is the contradiction. So that means that no such proof can exist. And that's what we were proving. Right. So this is the indeed the condition for. So we have proved S2. Now S3, as you can expect, slightly more involved. But let's discuss S3. But we are more or less in the end. So even if we do not present all the details right now, it's not that necessary. So important is that we more or less understand how the construction is.
There's a class.
But anyway, so there is nothing to record. So we will stop right here. So I think that gives you the idea about this whole proof. Yeah, that's it. So what can one also do with this construction? Prove the analog of second solvay theorem, where we characterize all sentences true in the standard model of arithmetic under such interpretations, but well, this is how it works. So now let us locate.
For next session, you will continue with that missed part?
No,
Okay.
no, I will not return to that proof because I actually think that it makes not too much sense to go into this particular detail. But, yeah.
Okay. Okay. That is.
Thank you very much. Bye.
Okay. Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you.
Thank you. Bye.
Taken by other group. So by everyone.